The simplex method is an algorithm designed by George Dantzig to solve linear programs. In technical terms, a linear program is an optimization of a linear function bounded by a set of constraints. A linear function is a summation of linear variables multiplied by coefficients. In its general form, it looks like this, where the a's are the coefficients and the x's are the variables. The linear function that we want to optimize is called the objective function. The constraints will be inequalities that the variables in the objective function have to obey. These inequalities form a space of values that the variables can assume without breaking the constraints. Therefore, the solution to the optimization must be within this space. Notice that the space will always be convex, since all of the inequalities are linear. This is an example of a linear programming problem. Before we can continue, the simplex method requires that the linear program is expressed in standard form. Any linear program can be converted into standard form using the following rules. We can turn any minimization into maximization by multiplying the objective function by -1. We need non-negativity conditions for all variables, so we replace those lacking one with the difference between two non-negative variables. Any number can be represented this way. We turn equalities into two inequalities. We change all inequalities to use the less than or equal to operator by multiplying by -1 where needed. Let's look at a more practical example. Imagine that we were asked by the mayor to decorate the local Christmas tree with a certain length of tinsel. You contact two local shops and they are willing to sponsor tinsel to advertise their goods. The first shop has red tinsel and will sponsor us £10 per meter to put the tinsel up. The second shop has blue tinsel and will sponsor £7.5 per meter. Our goal in this example is to get as much money out of the sponsors as possible. This problem can be converted into a linear program like so. We can assign the types of tinsel to variables. The objective function is the amount of sponsorship we receive. However, there are some constraints to take into consideration. We can't fit more than 20 meters of tinsel on the tree. The first shop can only give us 10 meters of red tinsel. The second shop can only provide 15 meters of blue tinsel. The mayor's daughter works at the red tinsel shop, so we need at least twice as much red tinsel as the blue one. In this case, we are only dealing with two linear variables, although there could be more. Here we have a 2D graph representing our problem. The horizontal axis is x1, while the vertical axis is x2. Each inequality partitions the space into two regions, such that all the points in one of them satisfy the inequality, while the points in the other one don't. Take this line for example. All the points to this side will satisfy the inequality, so the solution must lie somewhere in this region. In fact, our solution must be one of the points that satisfy all the inequalities. In our case, these points belong to a bounded region, although this is not always the case. If that happens, it is said to be unbounded. If there are no points that satisfy all of the inequalities, the program is infeasible. Our solution could be anywhere inside this region. We have to narrow our search down and find a place to start. Let z be the objective function. To get a good intuitive picture of this, let the coefficients in z be positive. Suppose this is the point that maximizes z. Notice it is inside the feasible region. If we add a constant to our objective function, we get a new line which is parallel to the previous one. The corresponding point on the new line gives us a higher value of z. We can keep on doing this until we intersect an edge, so the solution must be on the boundary of the feasible region. We can do even better and show that the solution must be at a vertex. Let's start with the shape of the feasible region. If it is bounded, it will be a convex polygon. This can be easily proved by induction. The base case is a triangle, which is the only polygon with three sides that we can form, and it is convex. However we draw a line that intersects it, which corresponds to adding a new constraint, the new polygon will still be convex. Since the space of feasible solutions is convex, and because all the inequalities are linear, such cases cannot exist. Thus, Going up or down an edge towards its endpoints will either increase or decrease the value of the objective function. This property can only change at the endpoints of a line, so the solution must be on a vertex. If it stays constant, we can pick any point on the line, so we choose a vertex. Let's solve it using the simplex method. The problem is already in standard form, so no transformations are needed. The simplex method starts by transforming the linear program from standard form to slack form. Slack form introduces a new variable for each inequality. These variables represent the difference between the right-hand side and the left-hand side of each inequality. Since the left-hand side will always be less than or equal to the right-hand side, these new variables will be non-negative. The variables on the left are called basic, while the variables on the right are non-basic. After this process, the only inequalities we're left with are between the variables and 0. Now we can start solving the problem. We know that the solution will be on a vertex. We also know that since the space of feasible solutions is convex, the local optimum will also be the global optimum. Simplex first finds a vertex and then moves to a neighboring vertex if it increases the value of the objective function. Once it stops moving, it has found the solution. To find the initial vertex, Simplex sets the non-basic variables to 0. If this point is in the solution space, we know it is a vertex because of the non-negativity constraints. Otherwise, it needs to perform an extra step to find a feasible vertex, which is out of the scope of this video. To move to the next vertex, we can increase the value of a non-basic variable until we reach another vertex. This operation is called a pivot. In practice, a single pivot works like this. Choose a non-basic variable in the objective function with a positive coefficient. Set all other non-basic variables to 0. Find the tightest constraint, that is, find a constraint that allows for the smallest maximum value of the variable. Rearrange the equation for the tightest constraint so that the chosen variable is isolated on the left-hand side, thus becoming basic. Substitute the variable with the right-hand side in all the other equations. Simplex then executes pivots until the objective function has no more variables with positive coefficients. This implies that we cannot increase its value further, since increasing the variables would lead to a decrease in the value of the objective function. Hence, by setting all the non-basic variables to 0, we achieve the solution. In our example, we start by choosing x1 as it has a positive coefficient. We then look at the constraints. The tightest constraint is given by this equation, so we rearrange it with x1 on the left. We then replace x1 by its right-hand side in all the other equations. For the second pivot, we choose x2. The process is the same as for x1. This is its tightest constraint. We rewrite the equation and substitute the right-hand side for x2 in the rest of the equations. Now we are left with no more variables with positive coefficients in the objective function, so we have reached the optimum solution. To complete our example, we set the non-basic variables to 0, which achieves a maximum amount of sponsorship of 137.5 pounds. To obtain this, we need to choose 10 meters of red tinsel and 5 meters of blue tinsel. This concludes the simplex method. In terms of time complexity, examples have been found with n variables and 2n constraints, where the complexity of the algorithm is big O of 2 to the n. However, the algorithm is efficient in practice and is widely used. For references and further reading, see the description. This video was made by Nicolas Audinet and Alexandru-Ioan as part of the Data Structures and Algorithms course at the University of Bristol.